Dear attendees, welcome to the webinar series on advances in mechanical engineering. And our first presenter of this series is Professor Ziad Saghir. And his presentation will be on innovative approach for cooling using water and nanofluids in channels. Professor Ziad Saghir is a full professor at Ryerson University and Canada's most experienced reduced gravity researcher. He has published over 200 scientific journal papers related to energy, and he is currently the chair of the International Conference on Thermal Engineering. So I'm giving you the floor, Professor Saghir. So feel free to start whenever you want.
Thank you so much, Professor Chopin, for this invitation, and it will be an honor to give you an update on what we are doing in the area of thermofluid. As my colleague mentioned, I am professor in the Department of Mechanical and Industrial Engineering in Toronto. It used to be called Ryerson University, but the name changed to Toronto Metropolitan University. What I'm planning to present to you today, it's basically what we are doing on the experimental and numerical side related to heat enhancement, heat extraction, or cooling system. And we are dealing with channels, mini channels, and porous media as well. So I will take you through 4 projects which we have done. And at the end, I will show you a little bit of the future one, which we are working on it right now. So if you do a literature review and you search in the paper, you see that heat enhancement, heat storage are very available topics to be studied in heat transfer, and they have a lot of industrial application. However, beside that, porous media also is an important area where we can use to extract heat. However, we have to always remember that from a mechanical engineering point of view, pressure drop is something we need to look at it very carefully. Also, you will see a lot of researchers which they have studied nanofluid, which is basically fluid with some nanoparticle, metallic nanoparticle. When the objective of it, they change the conductivity of this fluid so that it will improve the heat extraction. However, again, we have to remember that when we have nanofluid, we may have some sedimentation. If our channels are very thin, it will make a blockage. So all of those has a pros and cons, which we need to take it into consideration when we do the research. The 4 project which I would like to present to you is one of them related to porous media in general. The second one using channels and mini channels, and the third one, instead of using channel and mini channel, can we use pin fins? And finally, how can we use porous media, the thin layer of porous media in the channel to see whether this will help in heat extraction. The entire presentation, it's basically fundamental research, basic research. It has some industrial application, but so far it's mainly on the fundamental science side. Just a quick reminder, there are different type of method for cooling. The active method, one of them, it's jet impingement, and this is what one of my PhD students are doing right now. They use jet impingement in order to cool a certain surface. The fluid could be water, could be nanofluid. Or we have the passive method where we use some fins and we let the natural convection take away the heat from a hot surface. Now, on the active method, people have used with the jet impingement channels, whereby the channels act like fins or mini channels. They take the heat away from the bottom of a surface, and then the jet impingement cool them down. Or instead of putting channel, they use porous medium. You can use porous media with high permeability, and you will be able to extract heat using this technique. Or what you can do with the passive, you let it go by itself again using the natural convection. However, more and more we see more interest in rapid cooling. Therefore, the forced convection is the suitable one for this particular application. We've done some experimental work in channel, and the channel were 5 millimeter in openings, and the dimension of the experiment, which you see on the left-hand side, is equivalent to a computer chip, 3 centimeter by 3 centimeter. So we've done some numerical and experimental for those particular case of channels. And we had a kind of good agreement between the experiment and the numerical, and this helped us calibrate our code. Usually for our numerical part, we use COMSOL software, which is a commercial software available in universities. We also brought some, put inside those channels some porous media, and then we did some experimental work as well. And again, porous media, depending on the permeability, and here it's aluminum, and the porosity, it's 0.9, we're able to extract more heat than regular flow in a channel. Then from it, I would like to start taking you slowly into the four study which we did. One of them is what we did, we try to use nanofluid, and here nanofluid, we use aluminum oxide with water, and we had different type of application. One of them, the porous channel, which I showed you earlier, and in this particular one, it is a porous block. The porous block is 3.7 centimeter in both direction because it's a square, and the height is 12.7 millimeter. The work which we've done for this particular one has been published in Journal of Thermal Science and Engineering Applications. So basically, I will go into detail with this particular one. The second study which I'm presenting here is I reduce the channel by putting a layer of porous media at the side of the channel. That's the reason behind it. I want to reduce the pressure drop, because if we have a porous media, we'll have a pressure drop. So for this particular one, it was purely numerical after we calibrate our code with the experimental data, and we publish it in the Science journal not long time ago. The third study, we said, okay, if the pressure drop is the problem, what about instead of using channels, we use pin fin, and the pin fins could be circular or rectangular, and they form channel by themselves. And the reason behind doing this particular study is I would like to allow the flow not to go only straight through the channel, but circulate between the pin fins, and with the hope that this approach will create more heat enhancement, and this is the goal of the study. And we published a chapter in this recent Taylor and Francis group publisher, and the chapter related to heat enhancement. The fourth one, which we are currently right now doing, is what about the height of the channel? Although the cavity where the flow is circulating remain constant, I would like to vary the height of the channel and to see whether there is an optimum height which we can benefit from it. So we are doing two types of experiment in the study number 4, wavy channel and the straight channel, and all of them are made of aluminum. And I'm showing you the model, which also we are doing it numerically. So in parallel, we do experimental and numerical. So for the numerical, I will not go into detail. Basically, we solved the Navier-Stokes equation, full Navier-Stokes equation in 3 dimensions. And for the porous formulation, we solve using the Darcy-Brinkman model. However, I would like to stop for a second here and show you a future project we are doing right now, and then we are running experiment as we speak. It's basically, instead of buying a porous material, and when we do numerical work, we tell them we have a porous equation, we use a 3D printing, and with the work with the architecture department, we design a porous medium, and after designing it, we did a 3D printing, and then we are doing experiment with that. And on the numerical side, you don't need to solve the porous formulation. Instead, you select the model as being solid, and between the solid there is opening where the fluid circulates. So this is a new approach of dealing with porous media, and I will go into a little bit of detail at the end because we don't have data yet. Now, with respect to the study number 1, we did some experimental measurement for different heat fluxes. To remind you what is the study number 1, it was a porous block. And this porous material, you can buy it from industry, and they have a porosity of 0.91, and they have a different permeability depending on what you need. So we selected 10 PPI, 20 PPI, or 40 pore per inch. And we did it for different flow rate. So we are heating the bottom of the block, and we detect the temperature at the interface between the heated block and the channel where the fluid is moving. So we did it for a flow rate of 0.15 US gallon per minute, 0.1 US gallon per minute, and this is the results for nanofluid. And the concentration of nanoparticle here was 0.1% volume. And we had a good agreement between experimental and numerical. But one thing is very important to mention here is when you put your porous block to the hot plate, usually we put some thermopaste. And by putting thermopaste, we make sure there is a good contact between the heated block and the porous block. However, when you do numerical modeling, you must model this interface. And by modeling this interface, you can calibrate your thermal resistance for one case and use it for the entire correlation between experimental and numerical. Then we also changed the flow rate. We increased it to 0.18 and 0.22 US gallon per minute. And we notice as the flow rate increases, or as Reynolds number increases, then we start having differences between experimental and numerical, because at 0.3 US gallon per minute, we are in the transition zone between laminar and turbulent flow, and our model, we are keeping it on the laminar regime, so that somehow we start finding differences if we go above 0.3 US gallon per minute. And also we did it for a variety of nanofluid, nanoparticle concentration between 0.1% volume to 0.5% volume. And one thing you need to remember is when you do nanofluid in your flow, you must, when you finish your experiment in a single day, you must clean the system. And if you don't clean your system and clean the porous block which you are using, we will have some blockage. And the nanoparticle will be very difficult to remove it from this blockage of porous material. So for that case, this is something you need to take into consideration in your experimental work. Also, what we did, we increased the permeability from 10 ppi to 40 ppi, 40 pore per inch. And by increasing the permeability, then you see that the flow behaves slightly different in an unorganized way, and the discrepancy between the numerical and the experiment is obvious. This what let us believe that the new trend for doing flow in porous media from the numerical side is not to use Darcy, Brinkman, or those formulation, but to use AutoCAD or any kind of software to model your porous media yourself, and then you treat it as a solid in the numerical. So you still solve laminar flow, but this porous media become a solid block. And this is what we are doing right now in order to avoid some discrepancy between numerical and experimental. And again, we did it for, I'm showing you for another concentration of nanoparticle, which is 0.4% volume. Now, what we found something, I call it weird, strange, and we could not find the reason why it happened, although some experimentalists detected this issue. And you can see it's very obvious here. If you show the gradient of temperature between nanofluid and water, we notice that the best performance is for a concentration of 0.2%. In the beginning, we start doubting our data. We mixed different mixture of nanofluid with 0.2%, and we repeated the experiment many times. What we discovered that it does not make sense, or it does not mean increasing the nanoparticle will give you a better heat enhancement. So here I'm showing for 0.1%, 0.2%, and 0.3% for a certain permeability, for a certain heat flux and flow rate, and 0.2% is providing us with better heat enhancement than 0.3%. We repeated this experiment many times for different heat flux. This is another value of heat flux and another permeability, and again, 0.2% is behaving or is removing heat in a better way than other concentration. And again, I repeat myself, this has been detected in some experimentalists, but you hardly see it in other publications. Again, here I'm showing just the temperature variation, and you see that for 0.2%, the temperature variation or the temperature is lower than for the other cases of concentration of 0.3, 0.4, and 0.5. We have published this finding in the Journal of Porous Media and other journals. So basically, the message I would like to convey for this particular exercise, when you do experiment, nanoparticle tends to sediment inside the pores. So it must be checked that the porous media is always clear of obstacle. 0.2% for us, we found out that do a better performance than 0.3 than 0.4, which actually is good, because this what will happen, it will reduce the pressure drop 1, and then on the other hand, it will reduce any sedimentation or blockage into your channel or in your porous media. If we move to the study number 2, so after we calibrated our numerical code with the experiment, we start to study the effectiveness of, instead of using full porous channel, we use thin layer of porous channel at the wall, and we leave a gap between the porous media for the free fluid to circulate. And what we discovered from this exercise by doing it with water, we discovered that the pressure drop play a major role in improvement compared to a porous channel. And one way to observe that is if you take aspect ratio equal to 0, that means we don't have a porous media. If you take aspect ratio equal to 0.5, meaning the porous media is inside the entire channel. Between them is the aspect ratio where we have a certain thickness of porous media. And as you notice, the pressure drop is consistent with the thickness of the porous media into the channel. And then it varies, of course, as the flow rate or Reynolds number changes. However, we discovered that there is an optimum thickness of a porous media in the channel, which provide us with the best performance evaluation criterion. The performance evaluation criterion, it's basically a ratio between the average Nusselt number and the pressure drop or the friction factor to a certain power of 1/3. So by doing this, you will notice that from our exercise, we notice that the best performance for us is when the aspect ratio equal to 0.2, meaning there is a thin layer of porous media around the wall of the channel, and the advantage of it improves the heat enhancement, that's one. On the other hand, it also has an optimum pressure drop. So the ratio between both of them is the best candidate aspect ratio equal to 0.2. So this is a purely numerical model after we calibrated the experimental work. So that's the performance evaluation criteria is an important parameter which we need to take into consideration when we do this kind of analysis, because we don't want to have a good heat enhancement but a huge pumping power, because this defeats the purpose if we want to scale down our experiment. Third project which we did is basically, what about if we use pin fins? So we measure the temperature at the base of the pin fins, and here you see some crooked profile for temperature, and this is normal. The reason is at the point at the interface below the pin fin, we have a drop in the temperature. Then when the flow circulates between the pin fin, the temperature rises shortly, then drops. So this wavy fluctuation which you see, it's basically due to the pin fin. So at the pin fin base, we have good heat extraction, then it changed slightly. We also did it for a circular pin fin, and the idea behind the circular pin fin versus the rectangular, with the rectangular pin fin, you create more friction. And by creating more friction, we may have a higher pressure drop than for a circular pin, because circular pin flow around a circular obstacle has lower friction, therefore lower pressure drop. And one thing we did in this study, we vary the height. And by varying the height, what we are doing, we are encouraging the flow to circulate above the pin fin, and for the flow to circulate between the pin fin, and then they mix. And this is why we love to have mixing, because mixing will enhance the heat transfer without switching to turbulent flow. And this is obvious from this particular one, whereby when you have a full height of the pin fin, flow follow a certain pattern like channel. However, when the height is changing, we see some circulation on the top and on the side. And when it comes to the temperature, this is very obvious. You can see to the top one, for instance, we have a sharp temperature gradient coming from the heated block and then shooting up to the pin fin, and the mixing extract more heat in this particular one. So this attracted our curiosity, and this is the reason why in one of the study experimental, we are varying the height of the channel and the height of the pin fin. And when you look at the average Nusselt number, you see, of course, the better performance is when the aspect ratio is 12, meaning the fins are at full height, but they still have little bit of escape from the top for the flow to penetrate. But when you do the performance evaluation criteria, we notice that the block pin fin is doing a good performance, but not as good as the cylindrical pin fin. And the reason for that is the friction factor in the cylindrical pin fin is less. So this is the finding. And then what we also found when we looked very carefully to the data, we looked that there is an aspect ratio for which the performance is better for one or the other. So basically, the height can help in creating a mixing between the flow going above the pin fin and the flow going between the pin fin and reaching to the top. This mixing can improve the heat extraction. Then our final one, we are doing some experimental work. As I mentioned, we are doing some experimental work with the straight channel and with wavy channel and varying the height. And here's some of the fresh data which recently we submitted to a journal, and just to show you the temperature variation between numerical and experiment. And of course, as you can see, we have a discrepancy here with the experiment. We don't know why yet. We are still investigating. So we did the study for low flow rate, 0.1 US gallon per minute and 7.5 millimeter height. And then we increased the flow rate to 0.2 to 0.3. And then what we did, we tried to do it as well for full height, 12.7 millimeter and different flow rate. And we have kind of agreement between experimental and numerical. And when you look at the temperature between the 12.7 millimeter and the 7.5 millimeter, we notice that at 7.5 millimeter, the performance is slightly better due to this mixing. But again, this has to be checked very carefully before we judge. We come up with a final conclusion for it. The recent work which we are doing, we've done numerical, is one of them, we use conversion divergent channel. So up to now, we are using straight channel. So we use this model whereby we allow the flow to go conversion and diversion. And what we notice, it is the conversion channel is a good way to use because the flow starts very slow, and this is the place where the boundary layer, fluid boundary layer is very thin, and as the flow progresses, the boundary layer increases, but because it is a conversion channel, the velocity increases, meaning destroying part of the boundary layer as it leaves from the other end. Now, Professor Ho did some experimental work which we compared with him, but in his experiment, he did not have a diversion. He had only conversion channel. Here we allow both, but we noticed that the conversion is the most effective. And then we did also for different height, and we noticed that if we go to this particular height of 8 millimeter, it has the better performance evaluation criterion. The second project, which we just finished it right now, it's basically for wastewater. How can we use wastewater and try to take the heat from the wastewater and store it into the phase change material, which are located at the top and the bottom? And this is a very nice project because what we did, people, they put porous medium in the phase change material, or they put pin fins in the phase change material. Instead, we are focusing on how we can improve the flow to provide more heat to the phase change material. So what we did, we put pin fins and we put them in a chevron direction. And what we did, we vary the chevron height as well. And what we noticed is there is a certain height of chevron, which is 5 millimeter, not reaching the top of the cavity, do better heat enhancement. And it's interesting in this particular one with the phase change material, you see the block of phase change material in the top has a convective natural convection because it is heated from the bottom. And for the bottom phase change material, it's a pure diffusion process because it is heated from the top. I just published this recently in the Fluids journal with all the data are available. So this is finally, to finish my presentation, this is the block of porous material, which with the help of architecture department, it was designed, and they design it in such a way that they allow flow to penetrate, and the porosity in this particular one is found to be equal to 0.7. We are conducting the experiment, as you can see, studying the flow inside this. And then we did two types. We did aluminum printing. So it is a 3D printing for aluminum and for silver. So basically, we will look at different type of heat enhancement, but we were faced with a tough problem from the numerical side, because although we have the experimental experimental porous media with printing devices, 3D printing, but the problem was on the numerical side. When we try to take the AutoCAD or the SolidWorks model and then try to mesh it with a finite element, what the architecture people forgot about it is inside the surfaces, there were some sharp edges. And when you are dealing with finite element, sharp edges is not suitable. So, and it may not perform as it's supposed to. So we try to modify slightly and to make the curves more smooth, so that finally we were able to solve it numerically with our software console very nicely. And here you see the silver type of porous media. And now we have the capability of changing the permeability, changing the porosity. And when you do the modeling, we don't need to use any more Darcy or Brinkman or Forsheimer. All what we need to select is in the model, we say this is a solid. This is a solid, and the gap between them is the fluid will circulate. I am very curious to see the numerical and the experimental results, and we would like to compare those results with our first experiment where we had a porous media block and with the numerical to see the performance and to see which modeling is more realistic for industry. So in conclusion, I would like to summarize by saying porous channel are excellent way to do heat extraction. Channel by itself are very good way. Pin fin perform better. What we did as well, and it's not mentioned here, we put pin fins inside the channel. So in one hand, we extract heat from the channel, and the pin fin will assist in extracting more heat. And the other thing which would like to bring to your attention is, instead of focusing on how I can improve the conductivity of the phase change material by inserting porous media and filling the porous media with phase change material, or by putting pin fins inside the phase change material, keeping in mind by doing so we lose some volume of phase change material. let us concentrate how we can improve the flow and how can we improve extracting the heat from the flow to the porous media. With that, I would like to thank you for giving me the opportunity to listening to me, and then I welcome any question or answer from the audience. Thank you.